Hi, everyone, and welcome to our poster and presentation. My name is Jacob George, and I'm here to present to you What Can We See with DICE-CT, a comparison of iodine-enhanced brains and histological atlases in a rat model. My teammates on this project were Todd Green, PhD, Haley O'Brien, PhD, Dolores Vasquez-Sommerman, PhD, and Paul Genack, PhD. So introduction. DICE-CT stands for diffusible iodine-based contrast-enhanced computed tomography. And how it works is the iodine binds to fats and carbohydrates, enabling the differentiation between myelinated and unmyelinated nervous tissue. It's very versatile and can work on very small objects as well as very large objects. So it can work at high resolution too, at 1 to 100 microns at all these scales, and it's very cost effective. So, because it relies on X-ray technology as opposed to MRI, which is very expensive. So, for this study, you want to ground truth DICE-CT a bit against standardized methods and the Paxos and Watson Rat Brain Atlas. Our objective of this study. So, since we think DICE-CT may have the potential to become a standardized 3D brain imaging technology, to address these, we are pursuing short and long-term goals. In the short term, we hope to identify DICE-CT brain structures presented in the Paxos and Watson Rat Brain Atlas, and to interpret the reliability of viewing white and gray matter structures following DICE-CT preparation. Our long term is to generate a 3D DICE-CT rat brain atlas equivalent to the Paxos and Watson Rat Brain Atlas. For our methods, we began with our sample, which was one male Sprague dolly rat, and all excess tissues were manually removed. The brain chemical prep was beginning with 4% paraformaldehyde. The brain was then moved into a sucrose immersion. It was then soaked in Lugol's iodine, and following this, it was given a deionized water bath. The brain was scanned at the Micro-CT Imaging Consortium for Research and Outreach at 16 microns. Data was processed as exported TIFF files from the image stacks, and stacks were resliced to match the orientation from the atlas, and structures were scored by identification across 17 2D slices from all brain regions, and results were calculated as percentages by dividing the count totals per category by the count total from the diagrams in the atlas. So our results were based on these 5 categories. So category 1 is obviously the one we're looking the most for, which is for it to be distinct and replicable on both sides. A great example of this is the internal capsule. However, with the different myelination in different parts of the brain, you can end up with a lot of different appearances. So with this, we also had 4 additional categories: semi-distinct, distinct enhanced, distinct asymmetrically, and non-distinct and non-replicable. Now, as you can see, these pop up in all different parts of the brain, this kind of visibility. Our overall results were that gray matter structures were visible at 22% of the time, and white matter structures were visible nearly 60% of the time. So gray matter structures were distinguishable much less than white matter structures. And as would be the case, gray matter structures were much more likely to be non-distinct and non-replicable, and white matter structures were non-distinct and non-replicable only 22% of the time, versus gray matter structures at nearly 60% of the time being non-replicable and non-distinct. So our conclusions were, so greater than 37% of atlas identified brain structures, so this is categories 1 and 3, are routinely distinguishable, so that's pretty good, greater than 37%. A 2.5 times higher percentage of all white matter structures were identifiable compared to gray matter structures. So white matter structures were much more easy to distinguish. And tissue visibility appeared comparable to or greater than standard Cresswell-Violet histological sections. And future ground truthing includes additional sampling and comparing diced CT slices to other rat brain histological preparations and imaging methods. These are our references and our acknowledgements. And I'd like to thank all of you for looking at my poster and my talk. And if you have any questions, feel free to contact me.